Today, I first present some fundamental theorems that we will use in this course. And then we come to section 3.1 in the book. Section 3.1, bisection method. Bisection method is a method to find a root of a general equation. Okay, let me present the theorems that we will use in this course. The first theorem is intermediate value theorem. This theorem says that on a closed interval AB, a continuous, this is a keyword, continuous. The graph has low jump, low break. A continuous function f assumes all values between function value at left endpoint and function value at right endpoint. It's easy to understand if you know draw a diagram. Here is the xy plane. Interval AB, say here. Function value at A, this part, function value at A. Function value at B, this part. Yeah, function value at B. The function f assumes all values between function value at A and function value at B. Let me the graph is continuous. What? Between this point and this point, let me arbitrarily take a point. Say this point. Let me call this point L. Yeah. L. This is f of x. This height is f of b. L. Every point between f of x and f of b. Let me draw a horizontal line through L. Then, because the graph is continuous, the horizontal line must intersect the graph. Then, the function assumes L at constant. That means that function value at C is L. We say function assumes L at constant. Intermediate value between f of A, f of B, arbitrarily pick a point. They must be a point between A and B. Their function value is F. Because F is continuous. If F is not continuous, low this field. Then if function has a jump, not continuous. Not continuous. A jump. Then the function doesn't assume any value between f of x and f. First theorem. Second theorem, mean value theorem for derivative. Yeah, we often use. Second theorem, mean value theorem for derivative. If function f is continuous on the closed interval AB, and differentiable on the open interval AB. This differentiable means the function has derivative everywhere over the open interval AB between A and B. Everywhere the function differentiable. Then conclusion. Then there is a point C, yeah, between A and B in the open interval AB, such that derivative SC is equal to f of B minus f of A over B minus A. Or move B minus A to the left side. B minus A. Draw a diagram. It's easy to understand this here. AB interval. The function f is continuous. Yeah, continuous. Okay, continuous. Function is continuous and differentiable between A and B. Not this case. This function, the graph has a corner. And a corner function is not differentiable. Low derivative here. Yeah. The theorem requires continuous and smooth, low corner. Let me redraw the curve. Right? Curve, continuous, yes. And smooth, low corner. Low corner. Smooth, low corner. Few words. What is this quotient? F of A minus F of B over B minus A. It is the slope of this line. The line joins the two endpoints. Yeah, the quotient is the line. How to see? This point, x coordinate is B, y coordinate was already B. coordinate is A, function value A. The slope of this line, let me give a name, then A, B. Slope of line AB. Yeah, line AB. How to find slope of a line? We have slope formula. Y2 minus Y1 over X2 minus X1. Right? Do you remember that? Yeah. So Y2 minus Y1 over X2 minus X1. So this is slope of line AB. The line joins the two endpoints. Mean value theorem says that there is a point C, okay, between A and B. So then derivative at C is equal to the slope of the line AB. Derivative is slope of tangent line. Between A and B, I can find a tangent line whose slope is equal to the slope of the line AB. The two lines are parallel. When slopes are equal, parallel. Yeah. Where? Maybe here, about here. Tangent line, is parallel to this line. And here. And guarantee there is a C. Here, tangent line, slope is equal to slope of this line, parallel. Yeah. This is a mean value theorem. Yeah. Actually, we often use this equation. FB minus F of A. There is a C between A and B, so that this equation is true. We often use this equation. Double theorem. Rolle's theorem. We often use. But Rolle's theorem is a special case of mean value. Rolle's theorem. If function f is continuous on a closed interval AB, and differentiable on the open interval AB. Yeah. Graph continuous and smooth. And function value at A is equal to function value at B. Then there is guaranteed a point C between A and B such that derivative at C is 0. Special case. Yeah. Function value at A, function value at B, they're equal. Then the slope of the line is 0. Yeah. Special case. But we often the fourth theorem. Mean value theorem. Now it's time not for derivative, but for integrals. theorem for integral. And then function u and function v is continuous functions on interval AB. And one of them, and suppose then function v non-negative, okay, everywhere on the interval AB. Yeah. So between A and B, the graph of function v non-negative above x-axis. Okay. Now, then there is a point, say C in the interval AB such that this interval AB u x v x dx. Okay. We can find a point C between A and B so that we have two functions u and v. We can move one function outside the interval. Which one? U. U C A. Can be can equal to A and B. Yeah. Yeah. In this closed yeah, this is from section 1112 in the first book. Okay, now we turn to section B1. Bisection method. Section B1 by section method. Bisection method, we also call it interval Harvey method. It is because this method at each step cut interval in half. In chapter, this is chapter 3. In chapter 3, in the book, we consider to solve general equation. So f of x is equal to the function f log polynomial, log quadratic polynomial. Quadratic polynomial, we have quadratic formula for the solution. General arbitrary function, say how general, and e to x plus sine natural log x sometimes. So this is a single equation. And also we consider the solution of a system of equations. Say system of equations. F1 general, right? Unknown x1, x2, say xn unknown is 0. Second equation. And so on. Okay? N unknowns, we should have n equations. Otherwise, no. The n unknowns will not be determined. So n equations. How to find the root? What is root? Let me make this clear. If function at some point r is 0, we call r a root or a zero of the equation. A root or a zero of the equation. Chapter 3. Consider the solution of a general equation. Okay, now bisection method. Bisection method handle this case, a single equation. Not this case. For system of equations, no bisection method. Okay, only for a single equation. Okay. Bisection method has some assumption. Assumption. Yeah. Two basic assumptions to run bisection method. First one is we assume function is continuous. Yeah. And means over interval AB. But in practice, we have a function, no guarantee we know the function is continuous. But sometimes we know a function continuous. Say, velocity of a moving car continuous. But in some case, we don't know the function is continuous or not. Right? But this method assume function is continuous. And also assume function at A times function at B less than 0. What this means? This means the function in the two endpoints has different sides. Yeah, let me draw a diagram. Let me make the diagram. Yeah. A. Continuous, and at the two endpoints, the function has different signs. Say, for example, at A, function may be positive, at B, negative. Graph continues by intermediate value here. Guarantee. We guarantee. Yeah. The function has a root. Yeah, a root here. Yeah, root here. Guarantee. Under this two assumption. Intermediate value here says that the function assumes all the values between the two endpoints. Yeah. So 0 between these two endpoints. So there must be some R where possibility zero. Then R is called a root or a zero. Right, now bisection method try to find R. How? Okay. How? Okay. The following is bisection method. Bisection method. Under these two assumptions, step one, compute the midpoint of the interval AB. Yeah. Right. Compare midpoint. Compare the midpoint. Midpoint. How about let me use C center. A plus B divided. Okay. Now compute midpoint. Yeah. Let me use different one. A B and midpoint. About here. About here. Midpoint C. Yeah. We use midpoint as an estimate of the unknown root. Now, step two. Number two. Test if f of A times f of C less than 0. Yeah, this case is yes. Is it f of A positive, f of C negative? Yeah, this case. If this is true, then the unknown root is in left half interval. It's between A and C, right? Okay, now if this is true, then the root R is in the interval AC. Makes sense, right? And then set the new interval AB is equal to AC. That is for next step. Now, this case, yes, the root is in AC. So now I rename this C B. Okay. Then we have a new AB. Second possibility is, yeah, this is not true. If this is not true, if this is not true, then what? Then F A times F C greater than or equal to 0. Okay, and also under this F of A times F of C greater than or equal to 0 also has two sub cases. Sub case one, F of A times F of C is 0. Okay? F of A must be non-zero. Why? Because I know from the beginning we assume this. So F of A must be non-zero. So this implies that then C must be 0. And we successfully find the root. C is the root in this subcase. And now second subcase. And second subcase. And number two. Yeah. F of A times F of C greater than 0. Now the second case, greater than 0. Greater than 0. I don't know. Function at two endpoints, they have the same sign. No guarantee. The function has a root between A and C. Maybe the function has a root, I don't know, but no guarantee. But F and A times F and C greater than 0, that means that FC times FB must be less than 0. Yeah. Makes sense, right? So in this case, so the root is in CB. Yeah. Not this case, of course. Now root is in CB. Now, then we say the new AB as CB for next step. This is a one step of bisection method. Now, repeat this one step again and again. Yeah. Then now go to step one. Step one. Yeah, go to step one. Go to step one. Then complete part. Yeah. Of this new AB. Then test. Yeah. Repeat this step again and again. Then each step the interval in. So eventually we get a bisection. And here are some remarks by our bisection. The basic idea. Midpoint is an estimate of the unknown root. Bisection method to find a root, log fast. Yeah, the convergence rate is linear. Remarks. Hey, bisection method. Bisection method finds only one root. Between A and B, maybe the equation has more than one root. This is a possibility. Let me draw the graph. Say, hey, yeah. No, let me guarantee opposite sign at the point. See, if the graph like this, then bisection method has three roots. Yeah. Two roots. Three. Now, if you run bisection method, AB, then take big part about here. See, take big part. Now, function value in A, function value in C, greater than 0, they are positive. So, bisection method, take the second half as a new AB. Yeah, new AB. Then, half C. Right? Function value in A, positive. Function value in C, negative. Yeah. So the next new interval AB is new. So cut, right? Cut. C. F A positive, F and C negative. So the next new AB is this interval. Cut C. Functionality at C positive, functionality at B negative. So the next new AB is. So by system method, find this rule, not the other two. So only one rule. Now, second is how to know the midpoint C is close to the unknown root enough. How to know that? How to know? Okay. Remark number 2. How to know C is close to the root enough. Enough. How to know? The idea, okay, to know how C close to a root is, okay, yeah. Compute function value as C. Take absolute value. If function value as C is very, very small, then we consider C is the root. Second idea is okay. Second idea. Yeah. This is an AB. The interval AB always contains a root R. C midpoint. C midpoint. Yeah, midpoint is we use midpoint as estimate of the root. Hey, from this diagram, we can see that midpoint and arrow, that distance log greater than b minus a. B minus a is length of this interval. Half. Okay? Yeah. C minus r, is distance log greater than half of the interval AB from. Hey, now we can test this. If b minus a over 2, very, very small, and each step, the interval AB different. Yeah. At each step, we have new AB, new AB, new AB, new AB. If the length of the new AB take half, less, very, very small, then C and R very close. So we usually text these two inequalities. Then we stop. Of course, there are you can always find some extreme cases where these two inequalities they hold, but the midpoint C is still very far from the root. Easy to find such example. Say, for example, let me draw. See, take a look. Yeah. It's function. Now, let me draw this side. Here. Close to x-axis, the graph is flat and close. Then the root here out here. Suppose C is here, quite far from the root, and possible value is C in absolute value small. Possible value is C small in absolute value, but C far is far from possible. So in some extreme case, this doesn't guarantee C is close enough to the root. How about this case? Also no guarantee. Let me air root. The curve very steep. Very steep. Okay. Then let me draw a curve. Okay. Interval AB. You see, let me take an interval. A. Not this case. Not this case. Okay. AB is small. The center also close the root. Not this case. AB. In practice, here we require function f is continuous, but in some application, we don't know whether the function is continuous. And if the function is not continuous, we don't know. Okay, at the beginning we don't know. We just say now take an interval AB. Function value at A negative, function value at B positive, then run bisection method. Now this case, no matter how small the interval is, no. In some extreme cases, no guarantee. But in general, works. Idea. This is an idea. Now, the following is an algorithm. Okay. Computer algorithm. Right. If you write a code about bisection method, follow algorithm. First, input. What input? Input the interval. I want to find a root between A and B. And also input M integer. Say 100. What is M? Maximum number of steps we want to run bisection method. We don't want to run bisection method forever. Okay. M steps, then I stop the algorithm. Delta, small number. What delta? Is delta. And then epsilon, yeah, this epsilon input. Okay, now number 1, compute function value at A, store function value at variable U. Compute function value at B, store it at variable U, B. Okay, now compute minus B minus A, the length of the interval, store it at E. Yeah. Okay, now test whether bisection methods conditions are matched. Now step 2. If sine of U, yeah, sine of U, f of A positive, then this function, this meta function, will output 1. When U positive, output 1. I don't have time. Yeah, let me present this next time. Next time, no? Yeah. Yes. My office hours are Tuesday and Thursday. Go to syllabus, take a look, find out the time. Okay. So if you have questions about homeworks, yeah, please feel free to stop by my office. In my office. Yeah, I just assigned the first one. The first one, if you have questions, come and talk